Good afternoon. It's my pleasure today to introduce our speaker for the afternoon, Michael Cheadle from the University of Wyoming. Mike, he told me in his bio, well, I was at a bunch of old English universities. That means I had to look it up, Oxford and Cambridge and Cornell in between. So he was educated at those places. And when he was at Cornell, he was working on CoCorp things with the CoCorp group, and at Cambridge he worked on burps, reflection profiling, as well as doing his dissertation in melt extraction modeling. So he's got a variety of experiences in his education. Then he taught at the University of Liverpool for a number of years and has been at the University of Wyoming for a number of years, working on a whole variety of different things. He's a geophysicist, a petrologist, all-around interesting man with lots and lots of interests. And I think you'll find pretty fascinating what he's talking about today. The birth and death of oceanic core complexes and the largest normal faults in the world. Mike Cheadle.
Thank you, Keith. Thank you, everybody. I mean, I guess with that introduction, I should say that, you know what they say, jack of all trades, master of none, and I guess that's probably me. But what I'd like to talk about today are these things, oceanic core complexes, which are a relatively recent discovery. In the last 15 years or so, as we explore the oceans more and more, we've started to see these enormous normal faults. And really what I'm going to take you a run through today is a bunch of work that we've done some of it, and when I say we, my partner in crime is Barbara John, who's in the audience here today. She's ex-USGS, and a whole bunch of students, as well as Joe Wooden, that have been working on these things. But what I'm going to try and give you is a complete overview, as best I can, of what we know and what we don't know, and the still remaining questions on the topic as a whole. So some of this is our work, and some of it is the work of others. So to set up, the primary question is, really in the last 15 years or so, we've begun to realize that mid-ocean ridges are more complicated than we traditionally thought. And so on the left here, it's the classic picture that you'll still find in a textbook of the axial valley of a mid-ocean ridge, with these faults, normal faults either side, small offset dipping towards the center. And it's quite amazing, and that still is mostly the picture that we see in textbooks. But what we've seen more and more is this kind of cross-section emerging, where we can see normal faults with extremely large offsets. And this one's curling over, because the other thing about a ridge, it's hot, so the elastic thickness is very small. These things don't have a lot of strength, so they roll over, and you get these enormous offset faults. And so this picture is emerging to be more and more common, especially in the slow-spreading ridge environments. And so to follow that up a little bit, we can look at these pictures, which are just pictures of the bathymetry of the sea floor. What does the sea floor actually look like? And this is from a picture, these are freely available bathymetry, but taken from a classic paper by Buck in 2005. But here's the East Pacific rise. And the first thing to note on this picture is, here's the East Pacific rise. The vertical exaggeration is 15:1. So here's the axial rise, and it really is an incredibly smooth surface. You can see a few lines on here. These are faults. But basically, that ridge is incredibly smooth. And what's going on is, even though we're pulling the plates apart at an amazing rate, 16 centimeters a year, there's enough melt coming up that we're basically filling whatever hole we create. And so we pull the plates apart, melt's coming up just as fast as we're pulling the plates apart, so we end up with a smooth surface. As we start to slow down the rate of spreading, and here we've got intermediate rates and slow rates, topography becomes much more complicated. And if you look here, the vertical exaggeration on these are 5:1. So, just think about it. This is 3 times more exaggerated than these. The topography on the intermediate and slow-spreading ridges is much more complicated. And the simple answer is we're still pulling those plates apart, but there isn't enough melt coming up to fill the crack that you're creating. And so to accommodate that stretching, we're having big faults and big normal faults. And all these lines you see in this picture, which is your kind of typical, if you like, intermediate or even standard mid-Atlantic ridge type geometry, all these lines are normal faults. And then occasionally, and it's starting to become realized that these are more and more common, we get these much more larger offset faults, which are these things in here, these are our core complexes again, where this is a single normal fault that rather than having 500 meters of offset, might have up to 100 kilometers of offset. So we have started to recognize these things more and more in the bathymetry. And where do we find them? Well, here's a picture from a paper that Bobby and I put together now a few years ago, but all the red dots are oceanic core complexes. And you could look at there and say, well, there aren't that many, but to be fair, often the dot represents a length of the ridge where there might be literally 10 to 100 small segments of core complexes. And the fun thing about this game, and the thing that makes exploring the oceans interesting, is the reason there aren't any down here is because probably we haven't been there to look. So there's many, many more core complexes out there than you can see on that map. Those are just the ones we know about today. And as I've said before, one of the questions we're going to try and address in this talk is, why do we get them? There does seem to be a correlation with the rate of spreading of the ridges. And so as you all know, the East Pacific Rise is a fast-spreading ridge. The Mid-Atlantic is a slow-spreading ridge. This is an ultra-slow spreading ridge. And if we fade in a map of the spreading ridges over the top, you can kind of see that correlation. We tend to find these things where the spreading rate is slowest. And in this picture, that means the width of the color bars. Here, it's much narrower. This is effectively age. So, the same age from yellow to yellow over here compared to yellow over here means this one's faster. You're seeing them at the slower ones, because at the slower ones, you actually have got some sort of lithosphere. And the melt is having trouble getting through that lithosphere, and we're not getting enough melt to get through, so we're getting big faults to accommodate the extension. And in essence, that's the simple answer for why they're there. So I mentioned, I showed you those dots, so we just go back to the dots. Each dot represents an area rather than a core complex. So to look at an example of that, go on to the next picture. Here's just one small segment of 13 north on the Mid-Atlantic Ridge. Here's a 55-kilometer segment, and there's a core complex here, there's a core complex here, there's a core complex here, there's a core complex there. The whole segment is growing by these core complexes, not those parallel normal faults that traditionally we see in the textbooks. And here's a three-dimensional view of this particular core complex. You've got this big domal surface, characteristic corrugations, which we'll see more clearly on other pictures, but maybe you can see here, and then some sort of breakaway feature over here, breakaway fault over here. So, about 10 years ago, people would have told you only get these near transforms. What we begin to see more and more is entire segments. I said this is an entire segment, 55 kilometers long, just made up of these things. So they really are a fundamental component of extension at slow spreading ridges. Here's just another one, and we'll talk about some data from this one later on as we go through this introduction. This is the Cane Oceanic Core Complex. This is a bit further north than the one we were just looking at. This is one of the most, well-recognized ones. You can see the bathymetry here. There's a dome here, another dome here, another dome here. This whole thing is some complex. You can see these classic corrugations in the fault surface that seem to define these things. So this whole thing from this dash line to this dash line here is interpreted to be a single footwall to a normal fault that's been later cut by these high angle faults. Here's somewhere where we've been with a submarine. These red lines are submarine dives. And so here's pictures of what the fault surface actually looks like when you go to the sea floor. And guess what? It's relatively smooth surfaces with some sort of layering, which probably represents the anastomoving decimation and so on and so forth. Now, I mentioned right at the start the largest normal fault in the world, and we can argue about what that means. That was slightly me just trying to have a fun title. But the biggest one of these that's been found was found by the Japanese, and so they called it Godzilla. And it's found in the Philippine Sea, and interestingly enough, it's anomalous, of course. Well, actually, I'll take that back. Part of the problem here, we actually don't know the spreading rate of this ridge segment over here. But it's found in the Philippine Sea, and here it is. And if you look at this, what you're looking at, the first thing to recognize here is these are the big transform faults. So the scars that are coming from northeast to southwest are the big transform faults. Here's the ridge axis jagging around through these scars. So this is the ridge axis. So all these lines in here are the ridge parallel normal faults that we typically see in the oceans. But if you have a look in this segment here, you know, all the topography is perpendicular to these normal lines. And what this is a single fault surface. And so to put a cross-section on that to try and make that absolutely clear, here is the so-called breakaway down here, and this is the single footwall to one normal fault, which then disappeared into the ridge axis along this sort of line at the termination. And that's the biggest one we've found. It's 125 kilometers long. And if we look at the next picture for fun, you know, they're trying to justify that statement. Here's a picture of where we are now. Here's the US Geological Survey. There's a line that's 125 kilometers long. It goes somewhere east of Stockton. And so if we put that map on there, you know, that's how that would fit in the scale of, you know, where we're living today. Now, you can take issue with me saying that it's the biggest normal fault in the world. The active part of the fault is probably only about 7 kilometers deep, and we'll address that point later. But the exposed footwall at the end of this process was 125 kilometers long, and you can kind of guess the scale, you know, something like about 50 kilometers that way. So just to give you a feel for how big some of these things can be. And again, it's worth stressing, you know, about 15 years ago, we didn't know that these things existed in the oceans. So, what forms oceanic core complexes? And what seems to be the answer to that question is somehow one of these, if you like, normal faults seems to just get carried away with itself. In other words, you know, in a typical ridge, we break a normal fault, and then maybe the faulting jumps to the other side and pushes it away and carries on. For some reason that we don't fully understand, basically one normal fault just keeps slipping and slipping and slipping. And because the lithosphere is so thin, so hot at the ridge, we've got low effective rigidities, and so these things are just bound to roll over. They have no strength, they can't go up in the air, and so they just roll over and just keep going, and that's why they end up to be these big horizontal footwalls. You know, it's worth saying in there is, well, how do you define one of these things? As many of you know, the equivalent on the continents are detachment faults. We call these oceanic detachment faults. You know, as a rule of thumb, we start to call them large when the offset is more than 5 kilometers. But there's an arbitrary point to put in there to say, how do you define these things? So, what are the key questions that we've been trying to work on that we still don't have answers really for, which I'm going to try and address some of these in the talk today. First question is, why do they form? Why, in some cases, do we somehow localize deformation on a single fault for 125 kilometers rather than just jumping to some other fault? How deep do they go? I mean, how deep are they descending ultimately into the mantle? What is their rheology? What is their dip? Do they start off at low angle or high angle? And what do we know about their actual strength and how they work? Why do they stop? Which was a bit of the title that I missed off. How do we stop these things once we start them? Where does hydrothermal activity fit in? I was talking to Keith today, and he said, if there isn't an animal in the picture, it's not interesting, so there's got to be some animals in these pictures. And then lastly, you know, getting to the real, for me, interesting point is here's a cartoon of one of these things again. You know, somehow these things are rooting into the magmatic zone at the, you know, the axis of the ridge. How is this all related? I mean, you're in this world where your fault is almost certainly disappearing into a magma chamber of some sort, or at least into a crystal mush zone. And so how does that all work, and can we see that, and so on and so forth? So briefly today, I'm going to go through those questions and try and answer some of them, or at least point out what we don't know about others. So the first one, why do these form? And then the answer is, I'm not sure we really know the answer to that, but I'm going to talk about two distinct possibilities. And the first one is work, again, by Roger Buck at Lamont. And he came up with what's called a Goldilocks balance, that you've got this critical balance between faulting and magmatism. When you just have the right amount of stretching and the right amount of faulting, right amount of magmatism, then the faulting has to take over. And so he made this model which will produce oceanic core complexes, but the question is it a realistic model? But let's just hang with his model for a minute, and here's a cartoon of his model down here. What he said was, well, let's have thickening lithosphere. Here's the ridge axis at the middle. Let's spread these apart, at a symmetrical spreading rate. And then what we're going to do is we're only going to feed enough magma into the dike to accommodate half of the extension. And so the other half is going to have to be taken up by extending on a fault. And so this is where the model kind of cheats, because he puts all the magmatism on one side of the fault. And so on this side of the fault, this triangle in here is effectively stationary, because there's nothing to push this fault away. And so what happens is, as you pull these two plates apart in his mathematical model, magma is plating on this side to accommodate the 50% of the extension out there. There's no magma being plated on this side, so the extension is being taken up by movement on this fault, which then never stops, because there's no reason to cut a new fault. And so in this model, the whole idea is that there's some perfect balance between amount of magmatism, style of faulting, such that you can set up one fault that goes for a long time. It's the model that hangs out there that people like. But there's another possibility. And that's just simple kinematics. Because one of the things that I learned when getting into the marine community was plate motions change all the time. And so the question is, the hypothesis is, are these core complexes a response to changing plate motions? And in some places, that really seems to be the case. So let's look at the example of the Southwest Indian Ridge, which is this part of the ridge system down here. And here's a zoom in of that part of the ridge system 40 million years ago. And the cool thing about that ridge system is it's a new ridge. It's a propagating ridge. It's not the ridge that split Africa from Antarctica. This part of the ridge has been propagating across here. So nothing is inherited. We're not inheriting old transform faults from ripping off South Africa from Antarctica and so on and so forth. And so when the ridge was born, and this is a snapshot of it 40 million years ago, here's a ridge propagating up in this direction, spreading direction was something like that. We don't see many transforms because that's just how the ridge was growing in that direction. About 26 million years ago, massive change in spreading direction from northwest-southeast to approximately north-south. And so suddenly that ridge has got to re-accommodate how its spreading is occurring. And everybody knows from 101 textbooks, it's not completely true, but transforms like to be parallel to the spreading direction and so on and so forth. And so what we think happened is that this ridge segmented, like so, into little segments which are about 75 kilometers on average across, to allow this changing spreading direction to occur. About 12 million years ago, there was another subtle change in spreading direction. You can see it. There's a slight change in the orientation of that arrow, and that's important in the next picture. But the point is, once we'd set up this system of 75-kilometer segments, well, it was kind of reasonably stable for 26 million years. We can see from the magnetic stripe record that what's happening is some of these transforms are growing and others are dying. It's almost as though when we change the spreading direction, the lithosphere is in control. It's dynamically most stable to break it up into 75-kilometer segments. If you leave it for a long time, the asthenosphere, the mantle, takes over, and it wants to turn the system into these big segments, which are about 400 kilometers across. It's kind of what we see in the Pacific. And here's just our hypothesis of, if nothing else changes, maybe this is what the ridge is going to look like 40 million years in the future, with relatively big transforms, several hundred kilometers long, between segments of the ridge which are in parallel. Now, the reason we know this, try and get everything in today, I'm skipping slides, is we can kind of see this from the magnetic stripes. We can't see the future prediction, but these three steps you can see from the bathymetry and the magnetic stripes. And what I'm going to do on the next page is zoom in here and just look at this little area on the map, just where there's just this little offset here, and present some data rather than a hypothesis. And so here is that zoom in. Here's this big transform that is on the left. This is the Atlantis bank transform. Gives you a scale that's about 200 kilometers long. Here's the ridge axis. And if we just look at this bathymetry, you can see that there's a valley down here, which basically then died out and went away. This is a non-transform discontinuity, and which has gone away. And what has happened is when this part of the world was made, there was an offset on the ridge axis that was large enough that we were getting no accretion in there. And then by the time we get up here, this part of the ridge axis has moved north. We've actually reduced the length of that transform. And here's some real data as opposed to me hypothesizing. What we can do is look at the magnetic stripes on either side of this transform and measure the offset. And what you find is down here, the offset of the magnetic stripes is on the order of 15 kilometers. About 12 million years ago, that offset, which corresponds basically to this point in here, that offset decreases to about 5 kilometers. And up here, the offset, is 0 to 5 kilometers. So we've seen the ridge axis, this transform, this small transform, closing down about 12 million years ago. Well, the curious thing is what that means is the spreading has to be asymmetric. I mean, to make that happen, look at the spreading rate over here. If it's spreading at the same way to the south and to the north, we're not going to close this thing down. The only way we can close it down is if we start accreting more to the southern side of this segment than the northern side, which will enable this thing to migrate northwards. And that's where we cough out one of these core complexes. And we can see this in other parts of the world, and if anybody's got any questions about this afterwards, I'll show you another slide. But even that Godzilla core complex appears to be associated when we had a dramatic change in plate motion. So, are these things forming as a way of enabling the ridges to move to iron out transform faults and so on and so forth? It's another hypothesis that's out there for how they work. Okay, next question. What's the depth of these things? How deep do they go down? We saw that picture of Godzilla, which was 125 kilometers long. That's just the old footwall that's been exposed. How deep was the actual fault? What's the active part of the fault? And there's two ways of addressing this. Earthquakes, which other people have done, and I'll show you some pictures of earthquakes in a minute, but also geo and thermochronometry, which is what we've done. And here's a cartoon which explains the point. What we can do, these rocks inevitably have got zircons in them. So we can use uranium-lead dating of the zircon to get an age of the zircon when it cooled through 750 degrees C. We can also do uranium, thorium, helium on the zircon and get an age of the zircon when it cooled through, say, 100 degrees C. And we can simply look at that age difference between when it was at 700 degrees C and when it was at 100 degrees C. We can also use the evidence from magnetic reversals, which are also in here, which gives us a bracket from 550 to 250 in here too. And you can hopefully see the point if we compare these two pictures. Here's a picture where there's a big age difference between the uranium-lead age and the uranium-thorium-helium age. Here's the case where there's a small difference. What that means is if there's a small age difference, it means the isotherms are close together. If it's a big age difference, it means the isotherms are far apart. Once we get to about 900 degrees, we're beginning to get molten. That has to be the bottom of the fault. And so what this basically gives us a handle on is the depth of the fault. And in fact, for those of you that worked in the continents using things like thermochronometry, what the assumption is that if you know the thermal structure, then by measuring uranium, thorium, and helium, we can figure out uplift rates. Here we're doing the opposite. What we can measure is we can measure zircon ages along the exposed fault surface to actually get the movement rate of the fault, so we know the uplift rate. We can then use the chronometry to predict what the thermal structure is, and hence the depth of the fault. And if we look at some of the work we've done on this, this is one of the boreholes that have been drilled into one of these core complexes. So this is a 1-point data stops about here. This is a nearly 1.5 kilometer borehole in Gabbros in the middle of the Atlantis Massif core complex. Here's all the uranium-lead dates, so effectively equivalent to like a 700 degrees, 750 degree isotherm. Here's all the uranium, thorium, helium dates. And we're seeing two things here. The most important thing is just you can see what the separation is. I mean, ballpark, big error bars, but basically the uranium, thorium, helium is 400,000 years younger than the uranium-lead. It's taking 400,000 years for that bunch of rocks to go through the 750 degree isotherm and then reach the 150 degree isotherm. Interesting, down here, this age difference is getting bigger, and we know this is basically close to being correct. We can actually measure the temperature at the bottom of the hole today, and we know the bottom of the hole is about 100 degrees C. So you know the rocks, in terms of uranium, thorium, helium, are almost at zero age at the bottom of the hole. And what this means is we can take this data, and here are just some example plots, is each one of these corresponds to one sample. So one sample, up here at whatever that is, I can't read it, a few meters down, and so on and so forth. Here's the uranium-lead age. Here's the uranium, thorium, helium age. Here's this constraints from the magnetics, as I mentioned. Each one of these gray bars represents a magnetic reversal. So in the lab, we can effectively demagnetize these things and predict at what temperature the reversal is occurring. Because we know the age of the reversal from other work, we can use this to produce data points. And so we can do cooling. We can generate or predict these cooling curves for each sample down the borehole. And then we can put that together to come up with some sort of thermal structure for the fault itself. And I think the best way to think about this, here's a cross-section, so here's depth and so on and so forth. Here's the hole. But think of the hole as like a dipstick that's moving up. So originally that stuff was formed down here somewhere, and then as the fault moves, that green dipstick gets moved up through this thermal structure, recording the isotherms as it goes through it, as it cools. And so we can back out of all that temperature data to predict this kind of thermal structure. And the reason why the bottom is still hot today is top part of the fault gets ingressed with water and so cools off more rapidly than the bottom part of the hole. And so this gives us a constraint both on the thermal structure of the core complex and the depth to which the fault goes. And if you look at this picture, this is 0 to 10 kilometers. Down here at about 750 degrees C, it's when the rock starts to get mushy. You're starting to get into the mush zone. So we can see that the fault appears to be extending about, on average, 7 kilometers depth. Here, we're at about 2 kilometers. By the time here, we're at about 9 kilometers. So these stick down about 7 kilometers. And in fact, we've done this for several different core complexes, 3 different areas. This is the data we were just looking at. Here's another set of data at 15 North on the Mid-Atlantic Ridge. Here's stuff for that Kane core complex we looked at earlier. And what this is a plot of uranium-lead zircon ages against uranium, thorium, helium ages. So basically, the difference between these, how far these points fall off the graph, gives us a handle for the depth of the detachment fault. If they were the same age, it means the isotherms are on top of each other. The bigger the age difference means the further they have to travel to cross those isotherms. And so what you can see for all these core complexes, which are all in the Atlantic, is to a fast approximation, they're giving you the same sort of answer. That they're all about the same sort of depth. And in fact, we can start to put the numbers on there. For the one we just looked at, the age difference on average between the uranium lead and the uranium thorium helium is 0.44 million years, which corresponds to a 7.5 kilometer deep detachment fault. 15 North, 0.53 million years, gives you 8.5 kilometer depth detachment fault. Kane varies between 5 and 8 kilometers. So it gives us a feel. I mean, there's big error bars on these things, but these things appear to be extending down something like 7 kilometers plus or minus a kilometer. You could say to me, well, what about all these points that fall off the graph? Well, these are the ones that, there's a bunch of reasons why they might fall off the graph or off these lines. As we go down deeper, as we saw in the borehole, which explains these ones, it's going to get hotter. There's always a possibility in this complicated world in which we live, if we somehow reheated those rocks, we could reset the uranium, thorium, helium. It's just one of the problems we have to look through. But point is here, 3 different areas, some sort of consistency. Appears to be these faults extend for 7-ish kilometers down. And to briefly show the earthquakes, which is not really our work, there's not a lot, to resolve. The earthquakes are small. So to measure the earthquakes, you've got to go and set a seismometer array out there. This is one of the places that was been done. This is the TAG hydrothermal mound, TAG core complex. Here's a map view. This is the arcuate zone of the earthquakes. Here's a cross-section, and here's this zone of micro-earthquakes that they recorded. You can see what the dip is here. They've got about 70 degrees. They extend down to about 10.5 kilometers from the surface, which here is about 5. So basically, these things are extending down to about 5 or 6 kilometers, very similar to the results we were getting. But interestingly enough, the big question with this stuff is, what is happening up here? We're not seeing earthquakes in the shallow part. If this is the deep root of the fault, what's happening to the shallow part of the fault? But at least the earthquakes seem to be consistent with the depths that we're predicting. Okay, so depths of maybe 5 to 6 kilometers. Briefly, what about fault rheology? Well, if you pull these, if we go down in submarines and pull these samples back, they are classic detachment fault rocks. You see a big history of deformation, from high temperature deformation to brittle, shallow cataclasis. And so we can try and tease out all these different things, from trying to look through to see maybe what was hypersolidus, where the fault was playing with the magma chamber itself, going through high temperature dynamic recrystallization in both olivine and plagioclase, deformation amphibole, reaction softening to cataclasis. And we do see this complete spectrum from often within a single sample, and you can see this overprint of the more brittle stuff on the more ductile stuff. But to show you one example, and we've actually done lots of this stuff, so this really is just a snapshot. Here's one thin section. And the typical thing when you look at these things is you see strain localization. You see these narrow, high-intensity myelinite zones. And so here's just one example of these. I said this is a thin section. Here's one of these high strain zones. Here's a zoom in of the deformation in the plagioclase. And we do this thing called EBSD, which is measuring the crystallographic orientations of the crystals, which can give us an idea of deformation mechanisms, et cetera, et cetera. And so this one, the main thing to look at here is you just see some bullseyes. It's showing you that there's a fabric. It means that some sort of dislocation deformation is going on. And then we can plot that information on one of these things, which is deformation map. And so again, structural geologists have created these things. We've got shear stress along here. Point is, we can read off the grain size. And then if we assume the deformation is occurring on one of these piezometers, we can read off the grain size. We can put our circle depending on confidence on there. And then we can read off what the shear stress might be. And when we do that, we can start to then put together a picture for the strength of the fault overall, and maybe give an explanation for why there aren't earthquakes in the shallow depths. And so the overall cartoon model is something like this. So it turns out when you start to look at the rheology of plagioclase, as I said, once we get to about 900 degrees C, we're in the mush zone. So we're not going to record that deformation, because the deformation, if it's in there, is going to be the melt squirting around the crystals. But there's actually going to be only a tiny window in most rocks to have crystal plastic deformation. Because once you get in dry plagioclase from experimental work below about 850 degrees, it's going to deform brittly rather than ductily. And so, here's a classic sail diagram, which is our guesstimate of what the strength of these things are. All these blue dots are from the previous slide. Here are our shear stress guesses from that deformation map. Plotted, in some estimate of depth. This would be the ductile part of the deformation corresponding to the little green bit or the pink zone in there. Then we're probably going to follow some sort of Bailey's law with pore fluid, which, if we compare it to experiments, would compare to what we might find for serpentine. And then most likely to explain the absence of earthquakes in the surface, one of the things is that we're doing all this under 3 kilometers of water. And the water's getting into the fault. And the water is basically, changing the fault rocks. And so we're generating minerals like talc and so on and so forth, which again, from experiments people in this lab have done, we know are very weak. And so the lack of confining pressure up here and the fact that the mineralogy is becoming these very weak minerals possibly explains the lack of earthquakes that we see in the upper part of the section. But anyway, that's our best guess for the strength of these things. Now back to this thing, how do these things die? And again, we don't really know, but there's some fun observations to make. And in our flying around the world, we're going to go to one of the smallest ridges in the world. This is the Cayman Trough. This is a big pull apart, if you like. This is a big transform fold at the top, transform fold at the bottom, and there's a 100-kilometer spreading ridge just down the middle of it, which just by chance show you some wonderful bathymetry. And so here's a tectonic earthquake map. Here's what we're talking about. This just little segment, which is called the Cayman Trough. It's effectively a pull apart. You can see transform fault to the top and the bottom. One little ridge segment about 100 kilometers long in the middle. And this work was only done now 4 years ago. But basically, now it's become, in using an English joke, Clapham Junction of marine exploration. Just about everybody's been there. But it was a place that's been poorly visited until a couple of years ago. And what you're seeing here is a high-resolution bathymetry map of the ridge axis. So imagine, we're just in this box here. One of those big transforms is off the bottom here. The other big transform is off the top here. Here's the ridge axis. What you've actually got is 3 different core complexes at different stages of evolution. And it gives us a hint to maybe what happens to these things once they've formed. And the background to this, just a little bit of background to the ridge. This is one of the deepest. Because it's such a small segment of ridge, it's ultra-slow spreading. It's spreading at about 14 millimeters a year. It happens to be one of the deepest ridges. It became a really hot place because people found hydrothermal vents there for the first time about 3 years ago. And people chasing around that subject, what are the deepest hydrothermal vents in the world? Some of the deepest hydrothermal vents in the world occur just here. But also there's hydrothermal vents on this place, which is called Mount Dent, which we're going to look at in a minute. So let's look at this in a little bit more detail. Let's look at Mount Dent. This is the core complex in the middle. And again, to put a perspective on these things, let's compare Mount Dent to places that you might know. And so here's Mount Dent kind of looking side on, and Mount Dent up here in red. And OK, I cheated here again. Here's Mount Everest, true scale, but base level Tibetan Plateau. I mean, obviously, Mount Everest is much taller than that above sea level, but if you use the Tibetan Plateau as a base level, that's the size of Mount Everest. And many of you probably know the Ruby Mountains, so here's the Ruby Mountains in brown, and so it gives you the scale of Mount Dent. Mount Dent's about the width of the Ruby Mountains, but 1 to 2 kilometers high. Again, it gives you a feeling for how big these core complexes are. And what I want to look at here is, here's this bathymetry. There's a horrible exaggeration, maybe 3 to 1 here. But here's the side view of the core complex. Notice these lines up here. What these are faults. We're actually starting to see this core complex be cut in half. And lo and behold, can you see this ridge coming through here? This is the new axial volcanic ridge for the rift. And so hopefully I'll convince you in the next couple of slides. But what you're seeing here is the ridge is about to chop the core complex in two. And so here's a zoom out to hopefully start to make that clearer. Here's Mount Dent again. Here you can see these faults. Here's this axial volcanic ridge tracing all the way down through here. This is Mount Hudson. And so what we're suggesting is this is the future, if you like, of Mount Dent. Here are these cracks starting to form. Eventually, this thing is just going to get broken in two. And you're actually seeing this in Mount Hudson already happened 1 million or so years ago. And just to try and actually, I should go back to make that a little clearer. We actually went down here with a submarine to look at this ridge, and the next picture I'm going to show you is kind of a zoom in of this area. And even the bathymetry, you can see little volcanic cones, so we know this is volcanic. We dove here, we saw sheet flows and pillows. We know this is a volcanic ridge jumping through this thing. This thing has got something like 1.6 kilometers of throw. Really looks like the ridge cut through the middle of the core complex and split it in two, and that looks to be what's happening to the one to the north, Mount Dent. Now you could say, do I really believe that? Guess what? You see it elsewhere as well. Here's 5 degrees south on the Mid-Atlantic Ridge. Notice this core complex. Here's the corrugations, and here's the toe of the core complex. It's been ripped apart by the ridge. And so the question here really is this ridge jumping. Do we create these things and then the ridge can jump beneath them and tear them asunder? Or is something else going on, which I'll come back to later, which is coming back to that plate reorganization story I told you, the asymmetry of these things. So one of the things that we've been doing a lot of is actually trying to measure the slip rates of the faults. So simply, how fast are these faults coming out? And in principle, you can do that with the zircons, because if we can collect zircons along the surface of that fault, and then simply plot age of zircon versus distance, we get the rate at which that footwall was moving out of the fault. And we've now done that for 4 different core complexes. And other people have used magnetics to make the same argument. And so here's a diagram which is attempting to show how asymmetric these core complexes appear to be. And so just to explain this picture, here's 0 up the middle. And so basically what we're saying, this is spreading on one side of the core complex, this is spreading on the conjugate side of the core complex, the other side of the ridge. And so the point being that if it was symmetrical spreading, then the green bar over here would be the same length as the blue bar over there. And so what we're showing here is the red bar is where the measurement has been done by magnetics, the green bars are where they've done by zircons. This one, Godzilla, we don't know because we don't actually know what the other side is. So if we excuse Godzilla for a minute, the 5 that we've looked at, every one is highly asymmetric. In other words, 75% of the accretion at the ridge is happening to the core complex and only 25% is going out the other side. For the case of, this is a core complex on the Australian Antarctic discontinuity. Fuji Dome, Southwest Indian Ridge, it's 77%. Atlantis Bank, one we looked at earlier, 80% on one side, 20% on the other. Kane, 68% on one side, 32% on the other. Atlantis Massif, 85%. From what data, I mean, this is the world's data. If we believe that, if it stands up, it means that when you form one of these core complexes, basically most of the accretion is on the core complex and not on the other side of the ridge. If that's true, it's got a big implication, because it doesn't mean that we're slowing down the other plate. What it means is we're messing about with the ridge. And here's a picture which was actually originally drawn by Cliff McLeod in 2010, and I've modified it down here, but it illustrates the point. What you're looking at here is, here's our cross-section, here's some sort of magmatic source in the middle, and here's a little map. So here's our ridge axis and various faults on either side. We start generating a core complex. Here's the core complex growing. But because it's asymmetric, it has to migrate across the ridge axis. And so if you look here, progressively we can see it migrating across the ridge axis. And hence, and we'll look at this story in a minute, you often get a hydrothermal vent sitting on top of the core complex. And if you push it to its full extreme, maybe it's what we're seeing in that Mount Hudson picture, is then, if this really sets up as a robust magmatic system, it's going to rip the core complex in two and it will go both sides. So the point here is that if these things are asymmetric, and they appear to be, doesn't mean that the plate is suddenly speeding up. Really what it means is the core complex is migrating relative to the ridge axis, or we're pushing the ridge axis relative to the plates. So big consequences of that asymmetry. Okay, briefly. Rheology and uplift. I've mentioned before, these things aren't very strong. Kind of makes sense. We're at the ridge axis. It's hot down there. But here's Mount Dent again, and I'm throwing this one out as one of the things that I certainly don't understand. Here's Mount Dent again, a map. Here, and we're going to look at two cross-sections. Here's one across these ridges down here, which, best way to explain them is they're fault-bounded ridges. And here's one across the core complex itself. So let's look at a cross-section across here first. So the southern one first. And all these little crosses down here is actually the true bathymetry. So all these crosses in here, the true bathymetry. Well, actually, I should say the dense crosses are the true bathymetry. The more spaced out crosses out here of where we've extrapolated it from gravity. So here's the detailed bathymetry. And all we did is we created a simple flexural model. Very simple flexural model. We put in some normal faults with 6 to 7 kilometers of offset and simply measured this bathymetry with an elastic thickness of 1 kilometer. Point is, we can match those ridges reasonably well from the rheology you might expect and the amount of offset you can kind of see. Now let's look at that north line, which goes straight across the dome, and we have a big problem. Here again is the data, and here's the best we could do with the model. And if you look at this, you can see there's a mismatch of 1 to 2 kilometers. And this is found elsewhere. If you again go into the literature, you'll see people sneak. There's models in the literature doing the same kind of thing of other core complexes, but they don't model the ones that are really up in the air. So again, another question that we don't understand at the moment is, why do these things really get pushed up so far in the air? And this one you can see, Mount Dent gets to 2 kilometers below the sea surface. Some of these things are almost at sea level. St. Paul's Rocks in the Middle Atlantic, people might have heard of them. It's one of the places that the original discovery stopped at one time. That's a core complex that made it above sea level. So there's extra buoyancy in here somewhere. And is that magmatic? What is that? We don't know. It's one of the outstanding questions. These are too domal for simple flexural modeling. it remains one of the questions. I mentioned vents. Let's just do vents. We're going to do the animals to make the talk fun. Here's this volcanic ridge again, and these are faults that are beginning to emerge in Mount Dent. And lo and behold, here is a spectacular hydrothermal system, which was unknown up until about 3 years ago. People just didn't expect it to be there. Again, first hydrothermal vents were tended to be found on the fast-spreading ridges. People didn't really expect to find them in the slow ones. We zoom in. This is pretty much the same picture, just a little bit clearer. Even in this bathymetry, this thing is so big that even in this bathymetry, I've lost my mouse. I'll get there in a minute. Sorry, there it is. Even in this bathymetry, you probably can't see it. There's a little bump here. These things are several hundred meters across. You can actually see them in the bathymetry. But here are these faults, and this is where the vents are. Zoom in to see the vents. This is a order submap. What's happened here is we've put a submarine down towards a remotely operated vehicle, down towards the seafloor, and actually mapped them out. Here's the active one, which I'm going to show you pictures of in a minute. And then here's an old one. We went and investigated this one. These numbers are all where we went with the dives. This one's actually dormant, so, or dead. So, we're seeing a clear evolution here. But let's zoom in on this one and look at a nice 3D representation of that. That's what it looks like. And so, here's this ridge that you can see down here. To give you a scale, I'm going to show you a picture of the submarine on the spire. The spire is actually the chimney. The chimney itself is about 100 meters high. So this is several hundred meters high and half a kilometer long, something like that. And so let's zoom in and get the submarine view of it. There is the little Hercules remotely operated vehicle on the top of that chimney. And here you can see the big vent system. And again, one of the great things about this picture, when talking to the undergraduates, I always say, well, what do you think the white stuff is? Well, the white stuff is, and if I can indulge and take you guys on a little movie, if I can make this work on this. I'm not making this work. All right, let me see if I can do this another way. Best laid plans and all that. I see it. All right, let's skip the movie. Don't worry. We'll do some some close-ups instead. Let's come back in. I can't get it. All right, sorry, blown the movie. But we'll go on to the zoom in. This is what you would have seen in the movie, but animated. All that white stuff are shrimps, just millions and millions and millions of Rheology shrimps. Basically, living off the bacteria, which are chemosynthetic bacteria living off the vent itself. And we can zoom in and see what those really look like in close-up. This was all done for National Geographic, so it's some of the best pictures that you can actually see, but those are what the shrimps look like. So you can see here is a little vent on its own. Hot water is coming out here. This gray stuff is filamentous algae, which the bacteria feed on, and then the shrimps munch on the bacteria, and so on and so forth. And one of the most interesting things here is actually, it turns out this is one of the only place in the world where you can see both the shrimp and the tube worms. You've probably heard of tube worms on the East Pacific Rise. You don't find tube worms on the Mid-Atlantic Ridge. Cayman Rise is one of the few places in the world that you do. So it has importance for how things migrate and so on and so forth. But the message of our story is animals are cool, and you find these things on core complexes. All right, one last topic, getting near the end. All right, we've talked about these core complexes, but how does the crust actually grow at these core complexes? And so we're back to Atlantis Massif, which is this one at 30 degrees north in the Atlantic. And this is the Atlantis Massif borehole, which is 1.4 something kilometers long. And here's one of the, Bobby and I went and spent 2 weeks in the Bremen core repository and completely relogged this thing. Here's the rock types. The point is it's dominantly gabbro. The important thing to see here is you can see the scale of the variation of the composition, and I'll come back to that in a minute. The other thing, which is interesting, is that, all right, this thing is horribly layered, as you can see. I mean, there's all these different rock types. So you can go and measure those contacts. What's the orientation of the igneous lamination or the contacts of those things? And so other people, not us, carefully measured all those measurements down the hole. And this is everything you can measure. It makes no discrimination between an igneous lamination or a contact between a dike and or whatever. But what you can see, which is kind of curious, is everything or the majority of the points are all oriented at about 45 degrees. And that's the biggest pain there is, because the problem is when we drill one of these holes, the core can freely rotate. So we know today that it's dipping something like 45 degrees, but we have no idea of whether it's dipping towards the ridge at 45 degrees or dipping away from the ridge at 45 degrees or dipping parallel to the ridge. And that potentially is critical if we want to understand how that crust grows. Because if you just do the thought experiment, if present day it's dipping towards the ridge at 45 degrees, here's the detachment fault. If we basically take the fault itself back down to where it forms, it means those contacts form vertically. If it's dipping away from the ridge at 45 degrees, and we take the fault back to where it forms, it means those contacts are horizontal. So the fundamental question we're trying to address here is this crust growing by injection of sills, or is it growing by injection of dikes? We'll try and answer that. Before we go there, let's just give some feeling for the scale and the complexity of this thing. Here's the log again. We can just flash through this. Here's just a couple of example rock types. As a generalization, there are olivine-rich rock types. But the important thing I wanted to show you is this bar across the top. So in the 1.415 kilometer core, we measured 848 contacts. You know, in a core that's only this big across, it's sometimes hard to decide what that contact is. Is it, you know, a purely igneous contact? Is it an intrusive contact? So let's just lump them together for this purpose. If you do that, you end up with each unit being 1.67 meters thick on average, with the thickest unit being 27 meters thick. And if you actually correct it for dip, because remember, you know, the fault was inclined, so our present thickness is not the same, we come up with an average thickness of each unit, of each different rock type, if you like, of 1.2 meters. Now, I'm not sure what that 1.2 meters means. You know, I said we could have a layered sequence of gabbro that a geologist would say is 1 unit. But the point is, the accretion unit is very small. I mean, we are not having magma chambers that are, you know, 500 meters across. We're building this thing in maybe, you know, meter or 10 meter or 20 meter lumps, and that's the important thing. So, coming back to that orientation, sills versus dikes, the one thing we can use to try and reorient the data is magnetics, because we can always measure the magnetic vector in these rocks. And so here's the data before we do the reorientation. You can see it's just, these are poles to the foliation, and you know, they're plotted on this pole figure at about 45 degrees. And so we can quickly run through this. This is the present day attitude of the hole. If we then reorient using the magnetics, go to the next one. And so when the hole was formed, it was in this orientation. What we can actually find is those poles go to the edge of the perimeter of the pole figure. And remember, these are poles, so basically it's saying those contacts are vertical. And so, pretty much to finish off, and so actually, yeah, so here's the data over here. How do you do that? Only some subset of the data can we actually do this to, because not all of the data has magnetic measurements. And you can see there is some scatter, but there is a dominant location of the data, if you like, where the pole is horizontal and therefore the contact is vertical. And so, you know, our conclusion from this is the crust is dominantly growing in this sort of fashion by some sort of vertical dike intrusion and so on and so forth. And in fact, if that's true, it solves one of the big conundrums. People have seismologically tried to look for magma chambers at these things. You know, it's very hard to see a melt lens. Only rarely do you see them. But it's going to be very difficult if the melt lens essentially is a vertical structure. So that's about it. Rather than doing the standard summary slide that everybody does and read through it all, you know, there's still many questions to answer. We're getting there. We have got to be careful not to generalize. It becomes easy to come up with some overall picture for the whole thing when it's probably much more complicated, and there's still much to learn. And one last picture from that vent. Here's one of the shrimps with all its babies on board. Thank you.
So for your questions, please use the mic. We've got a mic on each side of the room. I'll ask a first one, and that is, what happens to magnetic stripes? across these things? They're dipping dikes?
It's difficult, and we've tried to play that game. One of the things that is always interested is especially these slow spreading ridges where people are starting to draw what's called a plum pudding model. So rather than having the standard picture of basalts over sheeted dikes over a layer of gabbro, what you've really got is plums of gabbro being injected into peridotite. And somehow, so people have done all the magnetics, but guess what? You can guess what the answer is. Often the magnetics is really horrendously complicated. And perhaps understandably so, because the gabbro might have the gabbro plum might have a magnetic signature, and then the peridotite might have a signature that's much younger related to serpentinization of that peridotite. So my 2 cents. So the easy answer to your question is it's horribly complicated. The interesting question is whether we could, at some stage, maybe if we can key it into seismology, where we can map velocities as well, and/or rock sampling to somehow interpret that complicated pattern to even give us a better idea of how we're building up this crust.
So one of the comments that you made was appealing to a very, very weak section of the fault near the surface and why you don't see earthquakes in your ocean bottom seismometers. And you said that you'd have to have talc for it to be that weak.
Right.
Do you see talc on the seafloor? Is there any?
Again, both one of the limitations and one of the fun bits about all this work is, we only pick up a small subset of what's down there. As I'm sure you know, much of the seafloor is covered by seafloor mud. You go there, you don't find anything at all. So the easy answer to your question is yes, I can give you rocks that have talc in them. And I think we even talked about that last time I was here. And I've been trying to get people to do experiments on those particular rocks. But I can't say to you that the entire fault surface is made of talc, because we just don't know. But there are definitely rocks we can pick up with lots of talc. Some of the most amazing ones were one drilling leg I was on, where the entire gabbro was replaced 100% by talc. The whole piece of core was just 100% talc.
Very interesting talk. In the simple Buck model, it seemed like the tectonics and the magmatism were completely separate in 2 different places. Whereas in your last picture, it looked like you have some sort of deep magmatic process that's accommodating this faulting at depth.
Right.
So it's a little more complicated than the simple geometric model.
So I think there's 2 questions there. You hit the nail on the head. So that picture I showed you from Buck was from 2005. So he and his students and other people related to him have gone on to do many more models. And there's a more recent one 2 years ago, 3 years ago, by a graduate student at Woods Hole, Olive, who did just what you said. Let's put some magma in either side. And still generates the core complexes. What I was trying to do there is to give the essence of the model. The way I'd prefer to think about it, which is maybe easiest, is that if we're pulling the plates apart and we're not supplying 100% magma to fill the gap, then we've got to have faults. The question really is, why do we have one single fault versus lots of faults? And in some ways, what they do, even in their complicated models, is prescribe that. And that's the bit that's, to me, unclear.
This is related to Ray's question.
Sure.
Earlier in your talk, you showed the fault systems rooting within the magmatic locus.
Sure.
In the middle of the talk, you showed the normal faults marching across the magmatic locus and not caring that it was there.
Sure.
And at the end, you showed it, again, rooting in the magmatic locus.
Easy answer to that is I don't know.
Okay.
Again,
I actually have a question, which is, do you see any evidence that magma likes to occupy that normal fault system?
Well, okay, so, again, in trying to cram things in here, we have done exploration of the footwall to try and map out what the footwall is made of. And often, and we see both peridotite and gabbro. It's a simple answer. And so some people will turn around and say, you know, that, well, the simplest, I'm trying to generalize here, we seem to have a picture of plums of gabbro within peridotite in the footwall of these core complexes. So a simple interpretation of that is at some stage, part of the fault system is somehow rooted into some gabbroic body at some stage in its life.
But does the magma ever choose to go up that fault system as opposed to going straight up to the surface?
Again, I mean, a great question, and I think that, and I'm not trying to put it off, I'm going to give you a partial answer in a minute. This is some of the things I don't think we fully understand, and I think that's cool. You can definitely find frozen, I'll use a British term, dolerite bodies actually within the fault zone in some of these core complexes. So yes, some magma is definitely getting into the fault zone. Now, whether it's coming up the fault or it's crossing the fault, I don't know. But there is definitely, you can definitely find, you know, fine-grained igneous bodies within the fault zone which are clearly part of that system. But how that, you know, I think that's partly one of the big puzzles. I don't know the answer to all these things.
A follow-up. Do you have footwalls that are dominantly peridotite?
Apparently.
That
I mean,
don't have a lot of gabbro intrusions in them?
Apparently. I mean, one of the, you know, so a little bit of background here. Actually, if I quickly go back. Sorry, give me a second. So the subject to this issue of it's hard to sample them because of the sediment on top. And, you know, one of the things we can do with seismology, and people have done that, is trying to measure the velocities. And the argument, though it's not 100% robust, is fast velocity equals gabbro because your peridotite is going to be altered. So if you can map out velocity and then make the assumption that peridotite has been altered, then the slow areas of the peridotite. But just quickly going back all the way, and there is an easier way to do this, but this is the simplest, right? Yeah, sorry. So if we go to Kane, which is what I talked about before, subject to the sampling, and this is why I wanted to put this picture up, as you can see where the dive tracks are in red and the dredge tracks are these little black lines. These two dimes appear to be dominantly peridotite. This one and this one appears to be dominantly gabbro. And that's really all I can say. So you will see in the literature cartoons which are dominantly peridotite. And I think, you know, you can take it to its end conclusion. If you go way up north to the Gakkel Ridge, slowest spreading ridge in the world, if we can turn off the magma supply, we have to just be bringing peridotite to the seafloor. And there's plenty of places in the world where we can find peridotite at the seafloor. But again, quite what the balance is in there, you know, it's all this fog of, you know, despite, for example, this dive track, which went all the way across the surface, you know, the grand total of samples we picked up was 16 because most of it is sediment covered. So it appears to be there's peridotite ones and there's gabbro ones. But you have to bear in mind our sampling.
Okay, well, if there are more, let's give Mike another great hand for a really good talk.